but the question about the fluctuation in the background radiation is the current explanation for why that galaxy's over there.
Yes, right.
And this one's over here. And there was a literal conversion experience in 1990 when the Kobe data was presented at that meeting in Florida, and they all of a sudden became big bangers.
As you stated, randomness is an assumption that most scientists just take for granted. And yet you and a few others, including myself, seriously question that assumption. How is it that you have come to that conclusion, if you can tell us briefly? And what significance does that have for the evolution of the framework that you're taking?
How did I get to the dark side? Well, first of all, quantum randomness has been the most controversial kind of thing contained in the quantum measurement problem since the beginning. Even the founders didn't like it very much, and yet it works so very well. But I was, I guess, first started thinking about this by some physicists. The one that comes to mind, it might not have been the first that I read, but anyway, Cerf and Adami, Nicholas Cerf and Chris Adami at Caltech, wrote a paper about this that's been widely ignored, and there are some other justifications for it in purely quantum theory terms. So that got me started. Then I started to think about it more and look at the evidence from psi for backwards causation. And for backwards causation, this suddenly solves the problem. So it clicked together for me, and the more I look, the more I see evidence that things are symmetrical in time. Preparation, measurement, exactly symmetrical. If you think about that for a while, and I think you have, a lot of things clear up.
Okay, unfortunately we're out of time for questions or discussion, so let's thank our speaker.